So this is Math 150, Section 1, Lecture Round 22. So we're going to continue our work with sequences and series. And so the big thing for today is to get to the comparison test. So the comparison test is one of the most useful, but it's also one of the hardest of the tests to use for whether or not a sequence converges or not. And the difficulty is you have to figure out what to compare it to. The ratio test, the root test that we're going to do later are much easier. There is also the integral test, and I'll give some idea of where that comes from today. For the integral test, you do also have to make the choice of what to use for the comparison, but for the most part, it's a search and replace. Every time you see the letter n, replace it with the letter x. Usually that works. All right, so a comparison test. So the idea is as follows. So we have some sequence an, and goes from 1 to infinity, of positive terms. So it's very important that the a's are positive. And we have two other sequences, sequence bn of positive terms, some cn of positive terms. And now we're going to assume the sum n goes from 1 to infinity of bn converges, and the sum n goes from 1 to infinity of cn diverges. Then the following. 1. If an is less than or equal to bn for all n large, what must be true about the sum of an?
Must converge.
It must converge. Why do I say for all n large? Why don't I say it has to hold for all n? So we don't need it to always be less than or equal to bn. We just need from some point onward, it must be less than or equal to bn. So imagine there was one point where an was larger than bn. And then for all other terms, an was less than or equal to bn. Just remove that one term from your sum. Remove that term from the an's, remove that term from the bn's. Will that affect whether or not the sum bn still converges? If you remove just one term? No. And if you remove just one term, will it affect whether or not your sum of the an's converge? No, so if I remove one term, it doesn't affect whether or not it converges or not. I can remove finitely many terms and not affect whether or not it converges. So you can always say, let's just start the comparison from some point onward. Maybe the beginning is a little bit screwed up and then things settle down. In Alyssa's thesis defense, player 1 has a winning strategy for n equals 2, and then from that point onward, player 2 always has the winning strategy. Something screwy happened in the beginning, but once you get past that, you see everything is fine. So I can affect finitely many n's without changing anything. All right, the next one is if an is greater than or equal to cn for all n sufficiently large, then what must be true about the sum n goes from 1 to infinity of an? It has to diverge. And informally, what's really going on here is, look, you're less than term by term a series that converges, and you're always non-negative. So imagine an was equal to -5 every single time. Well, if an is -5, it's always going to be less than or equal to the terms in a positive sequence, but then the sum of -5 would be what? It'd be negative infinity, so it wouldn't converge. So this is why really what's looking is the sandwich theorem. We're sandwiching an between two series that converge. It's always greater than or equal to 0. It's always less than or equal to bn. And so because it's always between them, it has to converge. The proof of this involves a tool from what subject or what class? Real analysis, right? This is not the linear algebra day, this is the real analysis day. So real analysis will give you the real tools you need to handle something like this. So I'm not going to give the full proof, I'm going to just give the hand-waving sketch. do we all agree that the sum can't be larger than Bn, than the sum of Bn? You're less term by term, so there's no way you should be larger than the sum of Bn. Okay, so we agree that this sum can't be larger than the sum of the Bn's. And we know term by term it's greater than or equal to 0, so it's got to be somewhere between 0 and the sum of the Bn's. So what you can do is, the proof is the following. Let Sn be the sum, n goes from 1 to n, of an. This sequence is bounded, and it's non-decreasing. Right? Because my ANs are non-negative, I clearly know Sn plus 1 has to be larger than Sn, or worst case, the same size if AN equals 0. So my Sns, my partial sums, are never going down. They either stay the same or they go up. All we have to do now is show that this limit exists. And this is just a property of the real numbers. If you have a sequence that is never decreasing, it attains its limit. Or as n goes to infinity, it hits the limit. So the question is, how detailed do you want to prove this? If you imagine, here's S1, here's S2, S3, here's S4, and they're marching up like this. So what we do is we say, what's the largest number we can take that's greater than or equal to all these sums? Well, we go all the way up to infinity. What's the smallest number we can take that's greater than or equal to all these numbers? We know clearly one number exists, the sum of the Bn's. So we know, maybe here is the sum of the Bn's. That will be larger than all the S's. And then we see how far down can we go. And we keep trying to move it smaller and smaller and smaller. If it ever hits one of the Sn's, then if any of the ANs was positive from that point onward, it would jump above. So the only way it could ever hit one of the Sn's is if all the ANs are 0 from some point onward. That series was not going to be interesting. So the question then becomes, how far down can we push this? And we take the limit of how far down we can push that. So is this enough detail? Is this convincing enough? It's basically, this is a property of real numbers, that if you have a non-decreasing bounded sequence, the limit exists. If it wasn't bounded, well, you could go up to infinity. So that's one. The second one is that if you're always greater than or equal to Cn, or at least greater than or equal to Cn for all n sufficiently large, then your sum diverges. Well, if I throw away finitely many terms, does it affect whether or not my sum diverges? No. So if Cn diverged, I could throw away the first Googleplex terms, and that's not going to affect whether or not the sum of Cn diverges. So I only need to know what's going on from some point onward. And if the sum of Cn diverges, it will diverge from any point onward. And so if An is greater than or equal to that, it will also diverge. All right, so we've done two cases. We've done An less than or equal to Bn, and we've done An greater than or equal to Cn. Are there any other cases we could look at? What other comparisons could we do? Yes?
You could do An greater than or equal to Bn.
We could do An greater than or equal to Bn. And what else could we do? Yes?
An less than or equal to Cn.
Okay. So if An is greater than or equal to Bn for n large, then what do we know about the sum n goes from 1 to infinity of An? Nothing. Give me an example where it will converge. An equals Bn. So if An equals Bn, you converge. Give me an example where it diverges. So what would be an example where it would diverge?
An equals n.
Ah, well that satisfy an is greater than or equal to bn for all n sufficiently large? We don't know. Or do we? What must be true about bn? Since the sum of bn converges, what do you know about bn? Yes?
The limit as n goes to infinity has to be 0.
Good, so we know the terms in bn have to be going to 0. So if we tried an equals n, that will diverge, and it will be greater than bn for all n sufficiently large, because the bn's have to go to 0. So this is a good answer. I'm going to show you a slightly better answer. an equals bn plus n. Now I don't have to worry about sufficiently large n. Do I have that result that the bn's go to 0? This is going to force it to be larger than bn. So again, there's a lot of different solutions you can do to problems like this. You want to get some feel, you want to try different things. So this tells us, unfortunately, that if we know we're greater term by term than a series that converges, that doesn't really help us. All right, the last one is if an is less than or equal to cn for n large, what do we know about the sum of an?
Nothing.
Still nothing. So if an equals cn, you diverge. If an equals what? What would give me something that would converge? Yes?
0.
So one possibility would be 0. That would work. So an equals 0, or an equals cn divided by cn plus 1 squared plus 4 times 2 to the negative n. Something like that should be more than enough to make it converge. Because now if I look at it like this quantity here is clearly less than cn. This quantity here is clearly less than 1. There's lots of different things you can do. I'm giving myself plenty of wiggle room, so if I've made a small mistake, it's still going to be okay. If you think about this, this is telling you your sum is less than positive infinity. It's not that useful to know your sum is less than positive infinity. I'm sorry, it's less than or equal to positive infinity. Less than infinity is useful. Less than or equal to infinity is not. So this is the comparison test. Of the four possibilities, 3 and 4 are useless for us. The ones we have to concentrate on are 1 and 2. We want to show that for all n sufficiently large, we are term by term less than a sum that converges, or for all n sufficiently large, we're greater than or equal to a sum of terms that diverge. The biggest mistakes people make when doing this is they try to use 3 or 4, or they don't check and make sure that your series an, your sequence an, is non-negative. So as long as you are aware of those, you should be okay. Okay, any questions on the comparison test? Yes?
Couldn't you just multiply the entire series by -1, and wouldn't all of those work for, and then all of the, then the comparison test would work for a negative series? Not alternating negative. Not alternating.
Right, so it would be a series that's negative term by term.
Yes.
So in that case, you would have negative bn greater than or equal to negative an greater than or equal to 0. You would still have something in a bounded, in an upper and a lower. So you would have something in that case, but if you have a sum that every term is negative, in some sense this is standardizing notation by pulling out the minus signs.
Okay.
If you think back to the quadratic formula, in the old days people did not like to write down the generic quadratic formula or how to solve a generic quadratic. They didn't like negative signs. And they would always have like a positive length as a positive area with some multiples. And so they would have the ax squared plus bx plus c equals 0. They would have all things on one side having positive signs and all things on the other side having positive signs, and there'd be no negative signs. They would just rearrange things. So in some sense, if you have a series where all the summands are negative, it's really the same as just pulling out that negative sign and playing these games. So really what's lurking in the background, and I'll just write it here, is the sandwich theorem. So let's see. So let's say we have Bn less than equal to An less than equal to Cn, and say greater than equal to 0. And let's say we know the sum of Bn and the sum of Cn converge. Does the sum of An converge? Yes.
Yes.
Okay, why?
Well, because when you use the Sam's theorem, like if something's in the middle of it, then it must be that thing which is bounded between them.
Wait, but maybe the sum of Bn is 5 and the sum of Cn is 8, so there's some distance between them, and maybe the An is doing some kind of strange dance. Now we hope that it's not doing a strange dance. We'd love to know if you are bounded on both sides by sums that converge, then you must converge. Well, let's think about what we know. What do we know? Oh, yes?
Well, can't we just go back to 1 from there?
Okay, but so how would we use 1?
Well, it's less than Cn, and Cn is converging. So wouldn't that also have to converge because the terms would be less?
Yep. So you could actually just apply 1. If you wanted to, you could even look at, no, that's the cleanest way of doing it, is you can just apply 1. Right? Does it matter that it's greater than or equal to something that converges? What do you call that?
Well, that was 3, right?
No, I'm saying, what do you call information like this that you don't use?
Useless?
No, there's a name for distracting information like this. Anybody know this? It's called a red herring. It's meant to distract. And so it doesn't really matter that I'm greater than or equal to the series that converges. Sometimes in problems like this, you might not even want to subtract the Bn from both sides, and then you get, 0 is less than or equal to An minus Bn is less than or equal to Cn minus Bn. But there's no need to do that. This is really just a special case of 1. All right, so let's do some examples. So unfortunately, in order to use the comparison test, we need series that converge and diverge. Unless you know examples, the comparison test is useless. So right now, we don't have that many series that converge or diverge. So we'll start making a list. Okay, so let me go just a little bit more. So series. Okay, and so we'll have converge over here, we'll have diverge over here. Somebody give me a series that converges.
1 over n squared.
We don't know that. We have not proven 1 over n squared converges. Yes?
R to the n.
R to the n. And what must be true about r?
Must be positive.
So if r equals 5, is that sufficient? How large can r be? So we need the terms to be going to 0, right? So when you look at r to the n, what's the only way r to the n can be going to 0 term-wise? So if r was 2, 2 to the n would be exploding. What must be true about the size of r if I want r to the n to be getting smaller and smaller?
Must be less than 1.
Must be less than 1. So as long as the absolute value of r is less than 1, the geometric series converges. That's basically all we know right now, other than finite sums, which are not interesting. What do we know that diverges? 1 over n. And that's it for now. So we really don't have that many examples. So let's add a few more. What if I gave you an is 1 over the square root of n? Does this converge or diverge?
This would diverge.
This would diverge. How do we know this diverges?
Because it's greater than 1 over n.
So this is greater than or equal to 1 over n. Let's call that our Cn. So we now would know that the sum of 1 over square root of n would diverge. And in fact, more generally, say an is 1 over n to the p is greater than or equal to 1 over n is Cn if p is less than 1. So they often call these p series. So we can expand what we have, and now we can say, 1 over n to the p less than 1. Now the claim you wanted to make was that the sum of 1 over n squared actually converges. And in fact, we do have the following. If p is greater than 1, then the sum of 1 over n to the p converges. We don't have that quite yet, but we can. So I'm trying to think if we can do this entirely elementarily. Probably the best way to do this is to quickly give you some indication of the integral test. So consider, I'm going to just do the case p equals 2 just to keep the algebra a little bit nicer. The argument would work in general. So consider the function f of x is 1 over x squared. And let's integrate x goes from 1 to infinity of 1 over x squared dx. So what function has derivative 1 over x squared?
Negative 1 over x.
So negative 1 over x, I evaluate this at infinity and 1. The negative sign, okay, when I put in infinity I get negative 0, and then when I put in 1 I get minus, so I get that this equals 1. So this integral converges. Okay? I can write this integral as the sum, n goes from 1 to infinity, the integral x goes from n to n plus 1 of 1 over x squared dx. Yes? Do you agree with this? I'm just breaking up my integration from 1 to 2, 2 to 3, 3 to 4, 4 to 5. So this is basically a precursor of the integral test. We're doing the integral test right now for one specific example, and then you can just modify this for more general cases. So do you agree that this integral with the sum is the same as this? So this must equal 1. When I look at this integration, if I replace x with n, I've made the integral larger. If I replace x with n plus 1, I've made it smaller. So this is going to be greater than or equal to the sum, n goes from 1 to infinity, the integral x goes from n to n plus 1 of 1 over n plus 1 squared dx. Right? Because I've taken the integrand and I've said, look, for each region I'm integrating over, let's just choose the smallest value every single time. Well, what's the integral of 1 over n squared from n to n plus 1? What's the antiderivative of this function?
Negative 1 over n plus 1.
Why negative 1 over n plus 1? What am I integrating against? What's my variable of integration? Right. This is a constant. Right? This is another one of the more common mistakes people make in calculus. It's keeping track of what's your constant. There's no x dependence here. I could write this as it's a sum, n goes from 1 to infinity, 1 over n plus 1 squared, integral x goes from n to n plus 1 of dx. Pull out the constant. And this goes back to earlier, when we were talking about the minus sign. Pull out the minus sign. Make the integral a little bit easier to look at. So I'm integrating dx from n to n plus 1. What will that equal? 1. And so now I get the sum from 1 to infinity of 1 over n plus 1 squared. So I get 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. So this sum is finite. Is this enough now to deduce that the sum of 1 over n squared converges? So it's not directly the comparison test. But if you think back to how we talked about how the comparison test was proved, if you have a bounded sequence that's never getting smaller, it's either staying the same or getting larger, and it's bounded from above, it has to converge. I'm adding non-negative numbers, and no matter how many I add, at the end of the day, I am strictly less than 1. I wrote less than or equal to. Could it possibly be equal? No. We know it's actually strictly less than. So we now know the sum of 1 over n squared converges. And in fact, was there anything special about 2? All that mattered was I needed this integral to converge. So if I put in any p that's greater than 1, it will work. So you can go through and you can just do the algebra. But this now gives us another example. So we now know for converging 1 over n to the p, where p is greater than 1. So when p equals 1, it diverges, and that's the boundary line. Anything greater than 1, it converges. Anything 1 or less, it diverges. So we now have more examples. So I'm going to do 1 or 2 more applications of the comparison test, and then I'm going to do some interesting applications of p-series. This is actually a very useful series to look at. Okay. So let's consider the sum, n goes from 1 to infinity, of 1 over 2 to the n plus n. So when you look at 2 to the n plus n, the thought is this likely to converge or diverge? Can somebody give me a reason why you think this might converge?
Because as I goes to infinity, 2 to the n is going to blow up and it's going to start at 0.
Okay, so, and we know the sum of 1 over 2 to the n converges. Can somebody give me a reason why this might diverge? It doesn't diverge, so I know the reasoning has to be a little bit flawed. But what's an argument you could make to say, I think this might actually have a chance of diverging? Yeah.
Well, 1 over n diverges.
Yeah, 1 over n diverges, so maybe this diverges because we have the 1 over n. Well, what's really going on is we have the 2 to the n, which overwhelms the n. The n is insignificant. So the comparison test, it's non-negative, so we just need to find something larger than it that converges. Can you give me an example of something larger than it that converges?
1 over 2 to the n?
Yeah, just 1 over 2 to the n. Right? So 1 over 2 to the n plus n is less than or equal to 1 over 2 to the n. So by the comparison test, we're done. The reason this was relatively easy is we have a plus sign here. So you say, yeah, look, just drop the n, doesn't matter. Okay, let's now consider the sum n goes from 1 to infinity of 1 over 4 to the n minus n cubed. Fortunately, we never divide by 0, so this is well defined. All the terms will be positive. What do you think, converges or diverges?
Converges.
Converges, why?
So I think the 4 to the n is going to dominate.
So we think the 4 to the n is going to dominate the n cubed, right? And this is a question of how rigorous do you want to be? If you are talking informally with a professor, not that rigorous. If you are taking an exam and your grade depends on it, rigorous. Right? So how would we make this precise? We want to find a series to compare this to. Now what's great is we have a lot of going on for us. We have a 4 to the n. That's much, much better than a n cubed. So we just need to show from some point onward, it's just destroying the n cubed. So there's a lot of ways to do this. One possibility is I can say, look, I can write 4 to the n. This is less than equal to. Do you agree with that? When n equals 1, you have 4 is less than equal to 4. When n equals 2, you have 16 is less than 4 plus 4. So do people agree that 4 to the, oh, sorry. Now do people agree that 4 to the n is greater than or equal to 2 to the n plus 2 to the n? What I'm basically trying to do is I'm trying to borrow decay, or borrow growth, depending on how you want to look at it. 4 to the n is growing so rapidly, what I want to do is, look, I'm going to take just a little bit of it to beat the crap out of the n cubed. And then the rest will give me divergence. So now, if I look at, 4 to the n minus n cubed, this should be greater than or equal to 2 to the n plus 2 to the n minus n cubed. We know 2 to the n minus n cubed is going to eventually be positive. 2 to the n, an exponential function, grows faster than a polynomial function. So this is going to be positive. So now if I do reciprocals, 1 over 4 to the n minus n cubed, we're going to make sure we do things in the right way. So if I divide by that, then that's going to be less than or equal to 1 over 2 to the n plus 2 to the n minus n cubed. And that's going to be less than or equal to 1 over 2 to the n. And that will give me convergence. So there's a lot of ways of doing this argument. I did another one in the video. What I'm doing here is I'm borrowing some of the growth to kill the n cubed. So to do this, we really need to know that exponential functions grow faster than polynomial. So this is a good time to review L'Hopital. So L'Hopital deals with either infinity over infinity or 0 over 0. We need to be in one of those cases. And if you're in one of those cases, basically the limit as x goes to infinity of f of x over g of x is the limit as x goes to infinity of f prime of x over g prime of x. And if you still have 0 over 0, infinity over infinity, you L'Hopital it again. And if you still have 0 over 0, infinity over infinity, you L'Hopital again. You keep L'Hopitaling. Okay? So for example, let's say we want to look at the limit as x goes to infinity of 2 to the n over n cubed. To see which one is growing faster. Well, we would need to take the derivative of both with this. Oh, I'm sorry, this should be x's now. The first thing is we have to take the derivative of 2 to the x. So you have to remember, what's the derivative when the exponential is not e? Or what I always prefer to do is just make it e. This is the same as e to the x times the log of 2 over x cubed. And you can look at this as e to the log 2 is 2, so that gives me my 2 to the x. So when I take a derivative, I'll get a log 2 e to the x log 2. And I'll get a 3x squared. So the first time, I'll get the limit as x goes to infinity. I'll get log 2 over 3 e to the x log 2 over x squared. And you can see the end is near. You can see the denominator is going to lose. Because the numerator hasn't really changed. The denominator has one smaller power. So we do this twice more, and we'll get the limit as x goes to infinity. We'll get a log of 2 cubed over 3 factorial e to the x log 2 over 1, and that's infinity. So this will tell us that exponential functions grow faster than polynomial functions. There's nothing special about 2. There's nothing special about the cube. As long as 2 is greater than 1. Right? If I give you the function 1/2 to the x, and I compare that to x cubed, it's going to lose. But as long as you have a base that's greater than 1, as you go off to infinity, it will grow faster. So exponential growth beats polynomial growth. The next one is, what about logarithm versus polynomial? So polynomials always beat logarithms. At least if you have positive powers. So just on focus. So now consider the log of x cubed versus x squared as x goes to infinity. So they both blow up. But it's which one blows up faster. And so we can do the L'Hopital argument all over again. But there's also a trick we could do. And here's the nice trick. Let x equal e to the y. I'm changing variables. As x goes to infinity, y goes to infinity. Now, the log of x cubed versus x squared, well, if I put in x is e to the y, this becomes y cubed versus, I put in e to the y, this will be e to the 2y. Which grows faster, e to the 2y or y cubed? E to the 2y. So we don't need to do anything. This is very similar to earlier in the day when I tried to give you the sandwich theorem. You said, wait, it's just the comparison test with a red herring. Mathematicians are lazy. Whenever possible, we try to reduce things to previously known results and do as little work as possible. I spent an hour moving tables to set up for the library book sale this weekend. I was the only one, I think, under 60 moving tables, at 8:30 in the morning. And the way it was working is people would have 2 people pick up a large, heavy table and carry it from the gym, through the corridors, through the schools, to the cafeteria kitchen. And this was long and consuming. And then I noticed, we have this little cart with wheels and 2 uneven parallel bars. We can just line up tables on this. And rather than moving the tables one at a time, let's just move massive amounts. Much, much faster. Whenever possible, look for efficiencies and look for ways to reduce things to things you've already done before. So here, we don't need to do a whole new set of arguments. We could L'Hopital this again, absolutely, but there's no need. All right, so we've seen a lot of nice techniques today. We've seen L'Hopital, we've seen the comparison test, we've seen that the comparison test can be a little bit tricky to use when you have something like this. But informally, what's going on is eventually the 4n is going to beat the n cubed. Let me show you another way to handle this without this delicate 4n is greater than or equal to 2n plus 2n. That's a hard thing to see. So let me show you an easier way to do the proof. So I'm going to use our fact that we know any exponential function eventually beats any polynomial. So we agree to the following. If n is large, n cubed will be less than or equal to 1/2 of 4 to the n. And the reason is if we look at the ratio of 4 to the n over n cubed, that goes to infinity. Right? We just saw that by L'Hopital. It's growing so much faster that when we look at the ratio of 4n divided by n cubed, that goes to infinity. Well, if this was greater than 1/2 of 4 to the n, then the ratio would be at most 2. So at some point, do you agree it has to be at most 1/2 times 4 to the n? So now, 4 to the n minus n cubed. So we always want to be careful. I want to get an upper bound for this. So I'm going to be taking the reciprocal of this. So if something is in the denominator, the larger it is, the smaller your number. The smaller it is, the larger your number. So I want to make this smaller than it should be. So worst case, this is 4 to the n minus 1/2 4 to the n. I might have subtracted too much. So then we would get 1 over 4 to the n minus n cubed is less equal to 1 over 4 to the n minus 1/2 4 to the n. Oh, but that's just 2 over 4 to the n. And this converges. So this is another way. There's a lot of different ways to do these arguments. It's what input do you want to use? How do you want to do the algebra? If you see splitting something like this, that's fine, but they're both essentially using the same idea. They're both using exponential growth beats polynomial growth. So here I'm having the 2 to the n beat the n cubed. Here I'm having 4 to the n beat the n cubed. And in both cases, I'm borrowing some of the growth, but not all of it. I'm just borrowing a little bit. Okay, I want to end with a fascinating sequence. There was a printing error, so I only have a couple of terms, but that's okay. Have we done Euclid's proof of the infinitude of primes in this class? Okay, this is one of the oldest proofs that has been continuously used, I think, in mathematics. It's been used for over 2,000 years. We will use slightly different language than Euclid, but it's essentially the argument going back to Euclid. So the claim is that there are infinitely many primes. So there exists infinitely many primes. If not, say P1, P2, Pn is all of them. We just list them all. So now, consider their product plus 1. There are two possibilities. It's prime, it's not prime. So remember, number is prime if it's divisible by exactly two distinct numbers, itself and 1. We don't consider 1 prime. 1 is a unit. If you're not 1 and if you're not a prime, you're a composite. Can P1 divide this? No, why can't P1 divide this?
Because you're adding 1 to it.
Yes, so the remainder when you divide by P1 is 1. Can P2 divide this? No. So none of the primes on our list can divide this. So either it's a new prime, or it's divisible by a prime not on our list. Not divisible by P1 to Pn. Therefore, either it's a new prime, or divisible by a prime not on list. So this gives you that there must be infinitely many primes. If you let pi of x be the number of primes less than or equal to x, this gives you basically, it's at least log x. The correct answer is basically x over log x. A lot of numbers are prime. It's 0% in the limit, but it's a lot of numbers. This argument, you can make it a little bit precise and get some count as to how many primes there are. It's bad. So what I want to do is I want to actually go through Euclid's argument with you. And at the nth step, it's going to give us a new prime. Let's list all the primes it gives us. So we start off with 2. So we multiply all the primes and add 1. So 2 plus 1 is 3. What's the smallest prime dividing 3 that's not on our list? 3. So we add 3 to our list. So the next stage, it's 2 times 3 plus 1, 7. What's the smallest prime that divides this? That's not on our list. 7. Uh-oh, what did we miss? 5. Will we ever get 5? Now let's keep going. 2 times 3 times 7 plus 1. What does that equal?
43.
Is 43 prime? Now this is interesting. So far, it's always generated primes. What do you think happens as you keep going? Or do you think it's too early to make a guess? Yes.
I think because all the primes are unaccounted for, eventually it's going to generate a number that isn't prime.
All right, so let's see. 2 times 3 times 7 times 43 plus 1. It turns out this is a multiple 13. So the next prime you generate is 13. The next prime is 53. The next prime after that is our friend 5. Thankfully, it does make it. After that comes 6, 2, 2, 1, 6, 7, 1. Now you can see why I brought notes today. Then 3, 8, 7, 0, 9, 1, 8, 3, 8, 1, 0, 5, 7, 1. Do you think we have time to do one more after this? All right, next one. Let me get a little bit more space. And the one after that is 139. This is a strange sequence. As you go further in science, you want to create new questions. What questions would you like to ask about this sequence?
Does it converge or diverge?
Well, what do you mean by converge or diverge? Because if you were to sum these are all positive numbers.
True.
And so, since they're all positive integers and they're all distinct, you always take the first prime not on your list, the sum will diverge. So we can ask that question, but that question is not too bad. What else might you want to ask about this sequence? So you have 2, 3, 7, 43, 13, 53, 5, 6,221,671, whatever that monstrosity is, 139. What might you want to ask about the terms of the sequence?
Whether we have this pattern.
Whether we have
This pattern, like why does it jump some numbers and then go back?
So why does it jump? Okay, so related to why does it jump, do we get every number? Is every prime on this list? We haven't seen 11. I think 11 is the smallest prime not on the list now. Will we eventually get 11? The next question related to that is, if yes, how long must we wait before we get a number like 11? If I look at all the primes that have at most 4 digits, can you tell me how long maybe I have to run this before I get all those primes? If I don't get all the primes, what percentage of the primes do I get? And you have to discover, what do you mean by percent? Well, you can say, well, let me look at all the numbers up to a certain height and see what fractions of the primes it gets. And then I'll divide that by the total number of primes like that. And then you can see how that goes. So there's a lot of questions you can ask about this, and I really want to get you to the point where you're asking new questions. So much of your competitive advantage in life is asking a good question. My wife is also a professor. She doesn't like the fact that I often say that 95 to 99% of my job is trained monkey work. Is that I've been taught how to use certain techniques to attack certain problems, as have other people. You ask any one of us how to do something, and if it's concrete enough, we know how to do this. This is very similar to the mechanical parts of homework. There was one paper that I wrote for my students when I was at Princeton. I could have been prosecuted for plagiarism. I was writing about the distribution of the leading digits of Fibonacci numbers, and I showed it had this digit bias we talked about. It turns out that somebody had already written a paper on that in the Fibonacci Quarterly. I was not aware of this, but the sequence of the lemmas and the arguments in my notes and this paper were almost identical. And the reason is once you choose to ask the question, the paper almost writes itself in terms of what you need to do. The hard part is asking a good question. And that's what I really want you to be trained to do. So whenever you see something, always ask, how can I push it? How can I generalize this? Where else can we go? All right, so that is a good place to end for today.